Right, welcome back. First video for quite some time, and this little video is going to be on the infinite series in Python. I might zoom in a tiny bit, maybe I've zoomed in too much. But basically, I saw this question on Twitter. I get a lot of questions on Twitter. This pi means the product of, so it's a mathematical notation for the product of. And the question was, what is the actual answer for this, or what is the sum of the infinite series? So maybe I'll sort of write that question down somewhere. What is the sum of this infinite series? Question mark. So that's basically the question that we have to hand. Now, in order to do this, I'm using a Jupyter notebook in this particular case, and I should probably just go through some of the mathematics. I have copied this over here, but really we're going to look at the computational stuff afterwards. So this is all just in a drawing application, so I'll just make a new thing here, and I'm going to do and I'm going to use Python's notation for power, although you could use a power like that, 2 to the power of n, and you could also do 2 to the n, and I would need to find a subscript here, so I'd have to have done something like character, I think, over here, and do, sorry, superscript, not a subscript. That would be 2 to the n, like that. So yeah, I could do 2 to the n plus 1. Maybe I'll stick like this for now, or that it already looks awkward, so let's just eliminate that. Just for simplicity, it's much easier to stick to conventional notation. So 2 to the power of n and then plus 1 over here like that. And we are going to take all of that, and we just then divide that by, I might as well copy the whole lot because it's just a 2 to the power of n minus 1. Just like that. And then what we need to do is we're going to take the product of all of this. So in some way, we're going to need to take the product of everything. I'll put it in curly braces so it's a bit clearer. We're going to take the product of all of this for n equals 1 to infinity. That's literally what we're going to do. I might put this on a second line there. We're going from n equals 1 to infinity. So what does that actually mean? We're going to start at n equals 1. And we're going to do this computation here. Which is just this over here. And then we're going to set n equals to 2. And likewise, we're going to do exactly the same computation, just like that. Now, if n equals 1, we've just got 2 to the power of 1 over here, and 2 to the power of 1 over here. And 2 to the power of 1 is actually just equal to 2. So that's just going to be 2. And 2 to the power of 1 over here is just equal to 2. And 2 to the power of 1, I forgot to put the minus over there. Be careful not to carry through errors. We're just left with 2 plus 1 divided by 2 minus 1, which is 3 divided by 1, which is equal to 3. So our first value for n equals 1 is 3. That's our first answer. And then when we've got n equals to 2, let me just get the spacing nice and consistent there. N equals to 2, we're going to replace this one, and I'll copy this down so we can get a few more of these in. Copy that. And paste it just down below, and a few more maybe. These will be dot, 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 some of them in between, so we get the hang of it. N equals 3, and then we can start replacing our numbers now. So 2 squared, we're going to have 2 cubed, and over here we're also going to have 2 squared, but this time it'd be 2 squared minus the 1, and we're going to have 2 cubed, and it'd be 2 cubed minus the 1, and we can start replacing our numbers. We know that 2 squared is 4. And 2 squared again is 4. So what we are left with is equal to 5 divided by 3, 5/3, whatever that is. I will pull up my calculator. Let's have a look and see if I've got my calculator somewhere. There we go. 5 over 3, turn 1.66 recurring. So 1.66. I'll put an R for recurring. Then we go n equals 3. We've got the same thing over here. 2 to the power of 3 is 8. 2, 4, and 8. And again, we've got 8 over here. And the numerator of this fraction becomes 9. And the denominator of the fraction becomes 7. So we're left with 9 over 7. And again, we can jump straight back to our calculator. 9 over 7. And that equals 1.28. 1.28. Now, recurring. Now we want to know what the product of all of these are. So the 3 times by the 1.66 times by the 1.28 and so forth. But let's just go to a very high number. Like, I don't know what we might consider to be a high number, but 2 to the power of 100. So if n equals 100, we'd have to stick it in here. And we'd have to stick that in here. And let's just see what happens when n is large. So I don't know if I can get 2 to the 100 on here. 2 to the power, 2 to the power of 100. There we go, some vastly big number. What I'm going to say is that this is equal to, and I'll just go on the next line here, this is going to be a large number plus 1, and that's the point of this, divided by a large number minus 1. And we can assume that a large number plus 1 is equal to a large number, and we can assume that a large number minus 1 is also equal to a large number. So we are left with large over large, and anything divided by itself is equal to 1. So this number is going to approach 1. So we are going to ultimately approach. I wonder if I can do that. Yeah, it does do, approaches the number 1. So that's what's going to happen when n equals large. We're expecting to observe this. Now we're going to translate this mathematics into something computational. We're going to be using the Python programming language to do this. So I'm going to set about doing it. The first thing that we need to do is open up a little block of code, and we're going to define a function. There we go. Define a function. It's our standard docstring for the function, and we're going to, in our docstring, we're going to say something like, given a value n, let us return. And I can actually copy some of the text that I wrote before, which is, we're going to return this, which is 2 to the power of n plus 1 divided by 2 to the power of n minus 1. But then after we've done that, we're going to find the product of it. So the product of all of those numbers, because this is what this pi actually means. I should really go through that final piece, which is once we've computed all of our numbers, this pi here means take the multiplication of all of those. And it looks like it's going to be something like 3 times 1.6 times 1.28. But then slowly, we're going to, for bigger values of n, we're just going to keep on multiplying whatever answer that we've kind of like arrived at. We're going to be multiplying that by 1, and maybe I'll be able to draw a quick Matplotlib lib chart or something to show a chart of it. But let's create this function. The function is going to take one argument n. I think it's an integer, so I'm just going to label it as an integer now. Yeah, in fact, it is an integer because n equals 1 to infinity. So we'll take this integer, and we're just going to return. And I think I can still do the same copying and pasting. Given this number, we don't have to do anything else. All we have to do here is just return 2n plus 1. Now we can go along and test our function. So we can say something like the result is equal to function, and then we'll pass in our first number, which is, say for example, number 1. And we just discussed earlier that 2 to the power of 1 plus 1, which is 3. Divided by 2 to the power of 1 minus 1, which is 1. 3 divided by 1 equals 3. So hopefully, if we print out the result, we should get the number 3. And indeed, we do get 3.0 over there. So that's highly satisfactory. That's very good. Now, we want to test this, say, for example, for our second number and our third number. So let's just do that. We could actually do a print here of the result like this, just to show it, and only because I'm going to extend this afterwards. So that does our first number, and then for example we want to repeat that for our second number. And again, we did this on the calculator and we saw that we had 1.66, which was this number over here for when n equals to 2. So let's just go along and print the result twice, and indeed we get the 1.66 recurring and so forth. Now, we could do this in a more succinct way. We could do this in a for loop, so for I in range, and then just do 10. Now, the one thing about this is the range function actually starts from 0 by default. If we did start from 0 by default, we'd have 2 to the power of 1 minus 1. We'd then get a 0 as the denominator, and it would throw us an error message because we're trying to divide by 0. I could leave that in there and show the actual error message that does come out. But let's just go along and do that. So we are going to print a bunch of results rather than doing it manually one by one. We're going to go from over, and we just got to make sure that we change this to an I rather than the actual number. So each element in there, when we do run this, we see we get this 0 division error, and we get the 0 division error because initially 2 to the power of 0 minus 1 is 1 minus 1. We don't want that, so we're going to start from range 1, and let's just say we want to get 10 numbers, so we've got to go to 11 because it's exclusive on the higher number. So we just run that, and we don't just want to print, maybe it's a bit more logical to print out I so that we know which number we're talking about. So we want to get 1 and the answer, 2 and its answer, 3 and its answer, and so forth, just to make sure that our function works quite nicely. And we can do that. And we can also see that we start at 3, then we go to 1.6, 1.28, 1.33 recurring, 1.06, but very fast we've only got to number 10 over here, so n equals 10, and we're already at 1.00105. So literally less than 1% away from 1 is the way to think about it. So we could continue that. We could stick in a much higher number, something like 101 over there, and our VS Code, or our notebook at least, it will put the triple dots there because it's not going to show every single number, but straight away we can already see that these numbers here, at least by number 25, and that's before it goes into the triple dots, so all of the other stuff is actually in the background. We could see it if we wanted to. There's potentially no need to. But what we can see is that there's a whole bunch of zeros there. So we're fast approaching number 1, and already when we've got to 100 over here, so 2 to the power of 100 plus 1 and 2 to the power of 100 minus 1, this number is extremely close to 1. It's so close that in fact to whatever number of decimal places that Python is rounding to is a good 10 or 15 decimal places, if not more. Let's have a little count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, about 15, I don't know, 15 decimal places. This, for all intents and purposes, is 1. So that gets us to that point there, but what we want to actually do is store these numbers in some way and create a product of them and see what that is. We just need to think about a smart way of being able to do that. So we could take our result and then just multiply it by the next result that comes out. I think that might be satisfactory to do that. So let's have a little think about that. One way that I can think to do this just off the top of my head is do something like next underscore result. And I could set that to the value of 1. Maybe there's better ways of doing this, so by all means throw this in. And I'm sure that you could do this in NumPy or something that's a lot quicker, but I'm just doing this using standard ranges because it's relatively simplistic. But if I set next result equals 1, then every time I do a computation for the function and compute the value for a result over here, I could just say that next result is equal to next result, and then times by the number 1. Now I could use the next result multiplied equaled to, and and that's going to be multiplied and equal to by result, like that. So I'm going to multiply next result by whatever the next result was, and the actual result. But I'll keep it simplistic still in this format. So next underscore result times the result. Now that's always going to take, I believe at least, that's always going to take the final result, and it's going to update it. So it can take whatever the last result was and it's going to update it by whatever the function computed. And I think that should be satisfactory. And if then in that case I was to do it like that, then we can do a next underscore result here in our print statement, and quite cleanly we're going to get the iteration number that we're on, then the value, the computation for the result, and then finally in the third element we're going to get one extra piece, which is the next result. Now hopefully the first one, as a tester, the first one will be the number 3, because we're just going to have a 1 times a 3, and then afterwards we're going to have a 3 times a 1.6 for the next one, and so forth. And maybe we can do like a back of envelope computation there, just knowing that we've got a 3 and a 1.6 and a 1.28. We can pull out our calculator just to predict what we might get. So if I do an escape just to clear out, I can do a 3 times a 1.66 and then times a 1.28, 57 say for example, and then times, oops, I just did an add on that, so I'll have to start that one again. 3 times by 1 point a few sixes times by 1.2857 times by 1.133. I don't know if some pattern emerges, but here we've already got to 7. Maybe the answer like terminates at 10 for example. Let's just see what happens anyway, and hopefully this little snippet of code works that replicates this function over here. And this pi here means the product of. If it was a sigma, which is a normal thing that we see, then we would be doing a plus just like that, but we're not doing that. We're doing a product of. So let's run our code, and indeed we get a 3, we've got 5, we've got 6, and then we've got the 7s. I think that was on the calculator, so that looked quite nice. At 1.3 we've got this 7.13, so with rounding I will forgive myself. So we were quite close on that as a guess. 8, and it looks like we're stopping at 8 1/4 there, and indeed that's what it looks like as an answer. We might go on for more, but here we see that we've got 8.25598, so we do this computationally rather than just numerically. We can do it both, and we can get a closed form answer, or I'm not sure actually, and those of you who want to go through the actual mathematics of it, I won't be doing the complete mathematics of it, although certainly you could. Is this answer actually, my question actually is this answer irrational, or is there a rational answer, i.e. is it going to approach 2.556 as the terminal value? And I only say that because this digit is, I see that this digit is increasing. One thing that I can do computationally quite quickly is add in an extra 0. So do 1000 loops and hang around. It still computes it quite fast. It took 0 seconds, and I can jump to the end there. I'm seeing that it iterates to 2.5987. So that's kind of like, we can see the repeated numbers now. In fact, these all seem to be repeated up to, they all seem to be repeated. So I am inclined to say that there is an irrational answer that's extended beyond that, but we know our answer to at least that many decimal places. So if you found this useful, I just found it quite interesting. I like doing infinite series. If you found this useful, then hit the thumbs up button, the like button, and the follow button. And if you have any comments as well, or the actual pure math solution for this isn't a math session, this is a computing session, but if you have the pure math solution for this with the irrational answer, if it was an irrational number, then by all means put that in the comment section too, because that would be quite nice as a finale. And that's basically it. That is our infinite series, our infinite product series in Python of 2 to the power of n plus 1 divided by 2 to the power of n minus 1, the product of that from n equals 1 to infinity.